is CO2. And in most of the cases, 5% CO2 is frequently used in incubators for maintaining pH in the culture medium. And the CO2 sensor in each incubator, it only works properly in adequately humid environment. So it is very important for us to keep the humidifier tray. You remember I told you about the tray which is placed inside the incubator on the bottom shelf. And this tray, we need to make sure it always has some water in it. Because the CO2 sensor, if it's not working properly, it will make the incubator have inaccurate level of CO2. And for example, it can make the incubator pumping too much CO2, which is much beyond 5% CO2. Or sometimes it will make the incubator to pump too little amount of CO2. In both cases, are not good for cells. So we need to make sure that this humidifier tray is always has some water inside. And that is very important. And we also need to examine our culture cells regularly, because when we start growing cells, we need to consider them like our baby. We need to take care of them, we need to feed them, and to check them at least on a daily basis. And this is some picture from ATCC showing you some cell lines at different densities. So at a high density, you can see some of the cells, they seem to grow closer to each other. And this is about, I guess, is about 50% confluency, meaning that 50% of the cellular surface is occupied by cells, and we still have another 50% empty space for cells to grow. And this is a little bit low density, it's about 20 or 30% confluency. And you can notice that this is a monolayer cell, so most of the cancer cells attach to the bottom of the blade. But some of the cells still floating around. You can see this is a round-shaped cell. And most of the time, those cells are dead cells. And so when we check the cell's culture, we need to check the culture's medium color based on the phenol red to make sure that the pH is still right. And to check whether the cell's culture medium has any cluster or precipitation or not. So because most of the time, the cell culture medium must be clear of and free from cluster and free from precipitation. We also check at a microscope to make sure that the cell doesn't have any contamination from bacteria, fungi, or sometimes mycoplasma. And if those contamination happens, so we need to treat the cells with appropriate antibiotics. And sometimes we have to throw them away and store a new vial and use new culture medium, new CBS, new systems. And also we need to tell other colleagues who grow cells in the same incubator and use the same good as us are aware of this contamination. Because contamination spreads fast and that can affect the workflow and the efficiency of the whole lab. So this is a serious problem if we have the contamination, and we need to tell people about it if we see any contamination happen. We also check the density. If the cells are too crowded, we need to pass them to another place. And we also check their viability to ensure that they are viable. Check their morphology and just make sure that they have the right morphology. They don't have any strange change in their phenotype. And check their proliferation rate. Because when we grow cells for a couple of, I think like a week, then we found no how fast they proliferate, so that we can predict whether that current proliferation rate is normal or not. If any change in the cell proliferation rate, then usually that is an indicator that something wrong with the cell, and we need to take care. Okay, so this is another microscopic picture of the cell, and this is the cell, the ND231 cell. This is a very toxic cell, and based on the cell, we predict the aggressiveness of the cancer cell. So you can look at this cell. This cell line, it has a spindle-shaped cell and very sharp, and also has a stretched pseudopods. So if you see these kind of pseudopods in morphology, then those are the indicator of the high cell high ability for metastasis in invading This subtle cell here is the broken fragment of cells, and this is dead cell, and this is live cell. So this is not a cell line of a breast cancer cell line, and you notice that this cell line, the morphology is different from the previous one. They are more shape, more rectangular. They don't have long pseudopods, and they don't have very stretchy morphology in pseudopods. So these cells, they are mostly a little bit less metastatic, less invasive compared to the previous cell line I just shown you. We also need to monitor cell growth and viability, and there are multiple ways to do that. The most classical way is to use the immunocytometer, and nowadays you can have some automatic cell counters, for example, like the mini counter, and in order to check cell viability, we can send them with carbon blue or other dye to evaluate the viability. So this is a typical hemocytometer, and this is another new device of Invision. This is automatic cell counter, and we can count them cells automatically using this machine, and we can first send them with carbon blue, and this machine will tell us not just the number, but also the cell viability percentage as well. And this is a picture of the cell looks like under the microscope after being scanned with carbon blue. And as you know, carbon blue is a blue dye that only cross the membrane of cells and enter cells when cells die. So these are the dead cells. All these blue spots you see here, they are dead cells. Because when they're dead, then the integrity of the cell membrane is damaged. So the carbon blue can get it easily and send the cells, and it becomes blue. But these cells, these bright cells right here, they are live cells. So using this symbol and method, we can distinguish the live cells from dead cells, and we can use the hemocytometer and the cell counter to determine the percentage of cell death and of the live cells. It is very important for us to make sure that our cell culture technique is appropriate, and also it's a very important technique for measuring cell survival. And such cultural cells meaning that transferring cells to a new place and feed them with a new media. And we need to do this step when the cell density is too high, meaning that it could be like 90% or 80% of the 100% confluency. And these are some of the basic steps we need to follow when we do culturing process. The first step is to warm up the culture medium. CDS is the first phase of buffer selling, and twisted EDTA from 4 degrees to 37 degrees using the water bath. And the first thing is, after all of this medium is ready for using, we also need to prepare the hood as well, like cleaning it up, sterilize all of the reagent we put inside the hood and also the glove as well. So the first step of such culture results, we will remove the old medium from old plate. And this old medium will contain the waste and sometimes dead cells as well. And we need to remove them using vacuum or pipetting system. And we need to wash cells with PBS, which is the first phase process selling, at least once. And this washing step is important to remove the waste from the previous culture medium. Also additionally remove the dead cells and also remove the SDS, because SDS can interfere with the subsequent crystallization steps. And after that, we remove CDS by vacuum or pipetting, and then we add trypsin, which is an enzyme that will help with cell detachment. And usually we add about 1 ml of unique to 1 centimeter dish. But the key thing is we just need to add 50 units enough to cover all the cells in the culture. And then we incubate cells with the plate about 2 to 5 minutes, 37 degrees Celsius, inside the incubator. And please notice that too long crystallization will damage cells, but too short crystallization will interfere with the cell detachment step. So the ideal situation is we crystallize the cells as little as we can, just until the moment that the cells start detaching, then we stop that reaction. So in order to stop the crystallization process, we need to add about 5 layers of complete medium, which contain the fresh SDS into the old plate. And the reason complete medium can stop the decrystallization process is because in SDS, in the fusible white germ, there is an alpha-1 alpha-addition, which is a factor that can effectively inhibit the activity of crystalline. And then after that, we mix the cells very well and transfer them into a new tube. And we take the tube out and start centrifugation about 1200 RPM for 5 minutes at room temperature. But this centrifugation step will depend on the centrifuge and also depends on each lab procedure as well. So this number may not be accurate in additive. But it is commonly used in our lab. So it really depends on which centrifuge you use and which cell type, then we're going to change this centrifugation rate. We also remove supernatant after the centrifugation cell. Then the cell will pellet down, and we're going to use the vacuum or pipetting to remove the supernatant, which is the solution of both the cell pellets. And after that, we'll send the pellet cells in 5 ml of new complete medium. And we transfer about 1 portion of the cell suspension into a new plate. And we add about 8 or 9 ml, or it depends on the size of the cell class, enough to make sure the cells have enough medium to survive. So we add the new medium to the same plate, and then mix the cells by pressing up and down several times to make sure the cells are in suspension and they are equally distributed in the plate. We put the cells back into the incubator, which has about 37 degrees Celsius and 5% CO2. And we clean all the model to tissue culture hood. We dump all of the biohazard trash in the biohazard trash bin. And please notice that at all times, that every single step, sterile technique needs to be applied. And the detailed procedure could change depending on the cell line, on the medium, acidity, and also immune optimization. It needs to be changed for our experiment. So I think that is everything I need to present about how to culture cells. And now I would like to show you a very quick movie that has been prepared by the University of Science, Stem Cell Lab. And